Hey everyone, welcome to our second week discussing evidence. This week we're going to be looking at selection bias, data visualization, and an example of big data. But in this video, I'm just going to talk about selection bias and some other common errors and things to know about numbers and data in general. So one thing that I like to point out is that in some sense, all numbers are made up. They're things we have because they're useful to us in some way, but we kind of make the rules for like what counts, what goes into the number. And some of these are useful, some are not. But like again, even some basic things, companies publish things like daily active users or monthly active users. What is an active user? How do we know it's a real person and not a bot? How recently do they have to have been active? What does active even mean in this sense? Like how active, right? Or, still relatively recently, there was a big issue with like when we try to calculate the coronavirus mortality rate, what's the denominator, right? Like, is it of all people who were at an event where COVID might have been present? Is it just people who checked into the hospital with coronavirus? And depending on what we want to know might depend on what denominator to use, but also these are measured with different degrees of error, right? Like if we attempt to say all people who had coronavirus, well, surely we're missing some people who had it but were asymptomatic, right? And we don't have a good way to count them. Like they themselves might not even know that happened. There is some like randomized testing you could do, medically speaking, and some of that was tried and all of that, but that's really a side note. The point here is just like how well we can actually estimate this depends on how we define it. But also we want our definition to not just be something we can measure, but something that is actually useful to us, right? And then there's the very important concept of like Goodhart's law, which is once we assign something as a metric, it ceases to be a good way to measure something because people are going to game it. And so initially we say, oh, well, standardized testing is correlated with all of these outcomes that we want. But if you then change the things you are doing to increase standardized test scores, maybe that correlation is not going to be there anymore, right? So once you assign something the status of a metric, the very things that made it desirable as a metric, like it being correlated to a bunch of other good things, may cease to be the case or may not be as strongly the case, right? A famous example is one of like giving a town that is infested with snakes some sort of monetary incentive where you're like, we're going to pay you every time you capture a snake. One way that people could respond, of course, is by killing and capturing all the existing snakes. But another way would be by breeding the snakes, like in their basements, and then turning in a bunch of snakes, right? So you don't want to have metrics or incentives that can be gamed easily and incentivize the wrong things. Okay, selection bias is just a huge thing that happens a lot, and so it's worth spending some time on. And the basic idea here is simply that when we go to measure something, the things we select out of the population might not have been selected randomly. And then there's all sorts of reasons this could happen, but one that we might care a lot about in a public policy class is if we have a public opinion poll, it turns out in some ways that people we're polling are all people who are willing to answer a question, whatever the question may be that the poll is asking, right? People who are not willing to answer that question, or perhaps not even willing to speak with a pollster, are not going to show up. And so there's some degree of selection bias. And it's somewhat hard to tell how big this degree is unless you have some sort of ground truth to compare your polling against. Not exactly an example, but one application of this that I think is useful to real life is this advice of like, don't compare your Google searches to other people's social media posts, which is to say like the things you see that people choose to write about themselves are not the same as the things that they choose to like ask for help about. Everybody Lies by Seth Stevens-Davowitz is just a really fascinating book. I recommend it if you have the time. Because it goes into a lot of this of like what do Google searches reveal about us and like what are the top 5 things people search on Google versus the top 5 things people post on, Instagram or wherever, in terms of just how different these are and how differently these make us look at like what it's like to be human beings, to the extent that we can, quantify that by how people are interacting with computers. So a small portion of what it's like to be a human being, right? One of the biggest and most common problems is selecting on the dependent variable. So like there are some forms of selection bias that are, none of it's good, but some of it might be mild enough that we're not too worried about it. But possibly the worst way to do it is say we have this outcome that we're interested in and we just select only people who already meet that outcome, because we're building in a correlation just by the nature of asking those people, right? So if you ask a bunch of successful people about what causes success and they say, well, I woke up early and I worked hard, and you then conclude waking up early and working hard causes success, there are probably also a lot of unsuccessful people, for whatever definition of success we have here, who also woke up early and worked hard, right? And I do want to acknowledge there's a problem with like how we're probably defining success in this scenario. But supposing we had some agreed upon definition, the point here is you could ask people who in the successful category, but in order to actually make fair comparisons and draw conclusions, you actually also need to ask people in the unsuccessful category. And then I already talked about polling in the beginning of this. Again, just an XKCD that I think really hits it well. If you always buy lottery tickets, this person who became rich by lottery tickets is making a speech about how they always poured money into tickets. But of course, most of the people who followed that strategy would just never win the lottery, right? But someone does. Someone has to. When I taught this in front of live classes, I used to have a coin flipping contest. And it turns out, like, with enough people, someone in your class is going to flip heads like 7 times in a row or something. And then I'd ask them how they became so talented at coin flipping, right? And of course, generally there's no actual talent there, right? It's a 50-50 coin flip. It's just someone's going to win. And again, that winner did nothing different in the coin flip case or the lottery buying case, where the results are truly random, than anyone else. But we go and we search for an explanation, and this happens frequently. So selection bias, definitely something to watch out for. Finally, I do want to do a bit of a quick explanation of the difference between machine learning and sort of classical statistics. And this is the best like simple diagram overview I've seen, really. In your sort of classical statistics or classical computer programming scenario, you have some rules, you have some data, you tell it how to get the answers. We're going to minimize the sum of squared errors. We're going to do some sort of statement, if-then statement maybe. In machine learning, you're going to give it answers and data, and it's going to come up with the rules. And this is actually very different. And to the extent that we're concerned with this in policy, where we're getting decisions about like how people can interact with, say, renting an apartment or any of the other sorts of like rules that we have as a society, we are now in danger of like these rules being determined in ways that may be incredibly biased. For example, Amazon tried this with training on hiring data, like here's the data, here's the people who had really good employment records here at Amazon and got good reviews. What are the rules by which we should hire? And those rules did in fact turn out to essentially be fairly discriminatory, which is, in my mind, an interesting analysis of like the current discrimination that is going on that led to those answers. But the problem is the rules can be opaque within machine learning. And so there's something where, you may get more efficiency, at least in the classical programming sense, from machine learning, because it's going to find the quickest way to get from the data to the answers, rules that we might not see or come up with ourselves. But that also means we've lost some transparency because we don't know what those rules necessarily will be, and we don't know in advance. And so then we have to make sure that we are doing analysis after the machine learning to figure out like what are the actual rules that are at play here? What is that path from like inputs to outputs? And is it a fair path, or is it something, was there something missing from the data and answers that we gave it that would lead it to be to produce rules that we are not okay with and don't want to implement? And so finally, I just want to say that like the upshot of all of this is that knowing things in the classical sense of like being experts in your field, knowing something about whatever your paper is on, say knowing something about immigration or about economics, or a specific area of economics preferably, then that still matters. Like there's not going to be I do not think there will be a time in the near future where it's just going to be like, oh, well, we've got the data, the machine's going to give us all of the answers, right? These problems are still really hard, and they still require a lot of time and effort to figure out and to really get into the weeds of and be able to say something useful.